Thank you, Arturo, for these very kind words. I nevertheless thought to start with a disclaimer because I don't want to hold the brain school hostage for all my wild ideas. And much of what I'm saying is caricature, like this first picture. This is the beloved, convenient paradigm under which people see environmental policy. It always ends with a good end. Countries start poor and clean, then they industrialize and get rich and dirty, and finally they end up being so rich they can afford pollution control, and they are rich and clean and everything is fine. The trouble is that for water or climate, this paradigm just doesn't work. Footprints, water use, greenhouse gases, etc., are rising with additional wealth. This is our present-day experience. And water consumption is actually rising even steeper, according to the FAO. And some of the water use is actually indirect, grey water kind of thing. We're using some 20 kilograms of textiles every year, and behind that you see 100 tons of water. And we have been talking about that in the context of food export. It's also a lot of grey water. Now, of course, many are now turning to reuse of water, which is very good. And LA County is proud of having that. But the effect so far is limited. Still, a lot of it is discharged into the ocean. The reclaimed water essentially is used for groundwater recharge, which is a good thing, no doubt. But I believe we have to go beyond that. And then much of the water reuse seems to be motivated by the aim of reducing the drainage volume. This I took from the Center for Irrigation Technology. If we are serious about the efficiency challenges, we just have to have one more look at climate change. Often people now refer to the IPCC report, which is legitimate. But the IPCC, in their bylaws, have a stipulation never to speculate, meaning they systematically exclude non-linear effects. And I'm talking now about one of the major nonlinear effects relating to the seawater table. You see that the seawater line is fairly bumpy. And here you see how much the effect is. In different times of heat, you have different coastlines. I chose not to show you the coastline for California. But now the main phenomenon that I find scary is the non-linear change of the seawater table as it has occurred in prehistoric times. When about 7,800 years ago, Labrador and the Hudson Bay were covered by ice like Greenland is now. Actually, also part of Greenland is, the Greenland ice is not on rocks but on water. So it's not stable by itself. And look what we are doing with Greenland these days. In a matter of 10 years, you see it's simply so much warmer. You have massive vertical streams of fresh water in summer running down the Greenland ice, lubricating the bottom. Imagine what's going to happen. So we just have to try and stabilize this dynamics. And the Intergovernmental Panel on Climate Change says, in order to do that, what we have to do is reduce worldwide carbon dioxide emissions by half or more. The Kyoto Protocol is at best good enough to stabilize emissions, mostly for the industrialized countries. It doesn't really address the developing countries. And stabilizing emissions means that concentrations go up for another 150 years. So we really have to go down. It's a huge challenge. How do we address that? Well, some say renewables, for instance, wind energy. I was Member of Parliament in Germany when we introduced this regulation, leading to the fabulous, really remarkable increase of wind energy. But that's the result, the thin green line. So it's just not enough. Now here in America, people talk much more about biofuels. But biofuels can be a nightmare, economically problematic. This is the nightmare. This is one of those palm plantations. Economically problematic. If you look at the prices for reducing 1 ton of CO2 using biofuels, you come to values of $100 or so, which is more than 10 times the present market value in the European carbon trading market of reducing a ton of carbon dioxide. So biofuels may be nice, I'm not against, but they are problematic. And then, of course, you have this problem with the tortilla prices. So essentially, the core of the answer, I say, must be a strategic increase of resource productivity. Actually, let me inject a word of terminology. Mostly, we are talking about conservation or efficiency. It's good, but this is a closed box kind of thing. If you have one task, for instance, illuminating this room, then you can ask how many kilowatt hours are we consuming for doing this task. Then you can talk about conservation or efficiency. I prefer to talk about productivity, which sort of opens the box into new avenues, into cascades of use, into changing the subject of not just illuminating this room, but doing other fine things with a limited amount of energy, as we actually have been doing with human labor. You know, 100 years ago or so, the shoemaker was making shoes, and his human labor had to be paid. But labor productivity did not increase by telling the shoemaker to be 10 times faster. No. But by inventing machines to do a similar job, not exactly the same job, much better. So I'm talking about paradigm shifts in thinking of making use of scarce resources. Therefore, I'm talking about resource productivity. Together with Amory Lovins, I was writing a book some 12 years ago on how to quadruple resource productivity. And the book, Factor 4, essentially consists of presenting 50 examples of how we can do 4 times better. Let me show some of them. This is Amory Lovin's favorite, the hypercar. Nowadays he calls it the revolution. I don't know why, but it's allegedly doing 150 miles a gallon. These are the so-called passive houses needing no active heating. They are now architectural standard in Germany, and it's something like 10 times better. My wife and I are actually building such a thing, a 4 generations house, my parents-in-law and we, and one of our daughters with her children, so it's going to be fun. Or we have the Brent School, also for office buildings. You can do a factor of 4 or more. And then next door we have Shuji Nakamura working, doing solid-state lighting, which is roughly a factor of 8 or 10 better than the incandescent lights. My friend Ryoichi Yamamoto from Japan, he was here in November, once gave me this right-hand picture steel, which in the production chain is more than a factor of 4 better than classical steel. This is the transport intensity of manufacturing strawberry yogurt in Germany, which is absolutely crazy. It can be replaced by more elegant methods. Then turning to water, there are dry composting toilets, which essentially use no water. Or you can recycle the water from laundries. Now, after Ed Fox has said that in Arizona they do already all this, I need not continue. I mean, there are all possibilities, and many of them are actually used, but not all. And then a moment ago I was talking about the grey water. Much of it is paper. We are using a lot of paper. Now, I looked into a German factory which increased the water efficiency for paper manufacturing by a factor of 12. Then the famous drip irrigation is up to 75%. This is also a factor 4. I don't go into details for that. And then, of course, the water recycling. I mean, this is what you have been talking about all the time. In India, the big debate is about rainwater harvesting. Actually, also in dry areas. So the Western United States would also be candidates for doing much of that. And then, of course, much less water is needed from centralized distribution systems. So the idea is to create a new Kuznets curve, built on the old one, but this time decoupling economic wealth from resource use, not only from pollution. But that's a long-term agenda. It may take 100 years. Essentially what I'm asking for is changing the core of the economic paradigm. The old one has been essentially about increasing labor productivity, which was a fine thing. I once sacrificed that. But now that labor is abundant while natural resources are not, I think it makes a lot of economic sense to go for higher resource productivity. But how do we make it happen? Well, of course, you can do CAFE standards and banning the incandescent light bulbs and the rest, and then, of course, education. Everybody's talking about that. But this is state language. This is not market language. If you want market language, you have to let prices speak. And now, labor productivity rose more than 20-fold over the last 200 years or so, and mostly in exact parallel with wages, with labor costs. It's well documented. And that would suggest then a strategy of actively elevating energy or water prices in parallel with energy or water productivity increases. Like, you could politically decide, at least in the European Union we could do that the end consumer price for such scarce commodities should be elevated by the percentage of increase of productivity in the previous year. Then by definition there would be no suffering. And yet, if this is a long-term strategy, all the investors in the investors community would go for aggressive increase of productivity, as they did with labor productivity. It's a lot of political engineering to do it. But in the end, all are benefiting. Well, in Germany we introduced, like in Britain, a gasoline tax. And indeed, you saw a decoupling in a very short period of time. But the real effect are long-term. I once looked at the OECD countries with more or less the same level of wealth and looked at the per capita annual fuel consumption. And there is an almost perfect negative correlation, meaning a almost perfect price elasticity. But this is only happening long term. The Japanese consistently had much higher fuel prices. And that made the bullet train profitable. And the US levels of gasoline prices, the bullet train would just not be built. It just doesn't pay. But if you announce that prices go up, then you will see the investors, even in infrastructure, also the state, of course, public money, to go into such things which make sense in the long term. Well, the last picture is essentially sort of the positive perspective of a new technological wave. If you look into the older cycles of steam power, electricity, petrochemicals, digital networks, biotechnology, and now it's sustainability. This is a picture I received from Charlie Hargroves of Adelaide, who is actually going to work with me on updating and completely rehashing factor 4, and next time it will be called factor 5. Thank you.
Actually, I conned my way into this talk two ways. When I first presented this idea to Arturo, he says, Bill, he says, we know you live in the excited state. I'm a free radical guy, all right? And he made me promise that I would stay in the lowest singlet excited state for my talk, and I agreed. And then he said, oh, and you have to talk about energy. Well, I agreed, but of course I don't know anything about energy. So I lied in both counts. And I think I'm going to start at the bottom and to say that this is kind of an overview talk. I looked at the talks, and actually maybe now that we've gone most of the day, it's probably better that I stay at a relatively easy level. I'd like to talk a little bit about water, advanced oxidation processes, which is my love, economic considerations, which I know nothing about, and then a paradigm shift, at least as I see it, as a technology developer in policy. So these are busy slides, and the reason was to try to cut down the number of slides. What do we know about water? Well, we know from our earlier talks today, population is going to increase, certainly within the state of California and the world for some certain amount of future. Water is essential for life and for a healthy planet, and I don't think we can forget that. The most important issue, I think, and I come from the drinking water side of the house, is safety of water. It's absolutely critical that we provide safe water. And then I think one of the largest unknowns in the equation is global climate change. It's very nice for us to be in a state that we've actually admitted that we're the problem. And I think that now, once we admit it, we can start to tackle it with increased funding to improve our understanding, predictive capability, and develop realistic solutions not only to global climate change, but also as they relate to water. We don't need to go through this. It's been mentioned ad nauseum, so I'm going to pop right into the next one. I think that water reuse is in fact one of the most underutilized and likely the cheapest, as we've seen in a couple of talks, in terms of water costs when we look at our total portfolio of water. As an aside, interestingly enough, we talk about how bad poop to tap is, but in fact in the late 70s they were practicing direct pipe-to-pipe potable water reuse in Namibia. The reason? They had no water. It's not something that can't be done. Technologically, it was there in the late 70s, and we know it can be done. So I think that water reuse is in fact a very much underutilized portion of the portfolio in water. So, and the other point here I would like to make is that once water is treated to a drinking water quality, it's such a valuable resource that we can't just dispose of it into the ocean, or, if you're inland, into rivers. We need to think about this whole concept of reuse. I do personally think that technology is in fact not the hurdle that we have to get over, but in fact The hurdles are more in the area of policy and a holistic look at economics. I developed I think maybe I'll just skip that. I'll come back to that in a second. Why advanced oxidation processes? Well, advanced oxidation processes are destruction processes. Those are processes that are defined by the hydroxyl radical right here. This is why I'm in the excited state most of the time. I start thinking about hydroxyl radicals. I get excited, and we destroy all sorts of things, including sometimes people around us. But AOPs don't merely just transfer a problem from one media to another. We actually destroy it. And what I mean by that is when we react endocrine disruptors with hydroxyl radicals, we destroy those compounds. I'm not sure yet about whether we destroy the biological activity, but we're actually working on that. But we know that we can get rid of the parent compound at the very least. The interesting thing about advanced oxidation processes in the more broad context is that they provide two barriers. One, they provide a barrier, this is in water treatment, to microbial contamination or microbial degradation of the water, and they also develop a barrier in chemical contamination. So we have one process, advanced oxidation processes, that has multiple benefits and multiple barriers. And if you're in the design of water and wastewater treatment plants, you're always looking at multiple barriers. And they are also very effective against very low concentrations of these emerging contaminants. And the problem, so one of my hats I wear is also as an analytical chemist, which really angers a lot of our colleagues, because we're now able to look at chemicals at much lower concentrations than when I first got into this game in the early 70s. As a result of that, we're now being able to quantitatively tell you how bad the quality is of your water. Only from the point of the number of chemicals that are formed, not necessarily whether it has any adverse health effects. And the last thought I would like to leave you with respect to advanced oxidation processes is that there are also processes out there that produce reducing species, in chemical terms, hydroxyl radicals and oxidizing species. So we're now starting to think of advanced oxidation and reduction processes, and that even extends the applicability to those processes to a wider number of organic compounds that are found in waters. So what are advanced oxidation processes? We're kind of getting away from the energy theme here for a second. Ozone, ozone UV, ozone peroxide, TiO2 and light. This is just this is a really interesting process. Fenton's chemistry, actually first described in the 1890s, so it's a relatively new process. That's 1890s. Senolysis, UV, hydrogen peroxide, in the process that is near and dear to my heart, the electron beam process. And I won't tell you what we call it in the bar. Or unless we go to the bar, of course. The electron beam process, as an example of an emerging advanced oxidation process, it's so frustrating to give a talk when the first question from the audience is, well, how much does it cost? When I'd really rather have them ask me how efficient is it, or does it do the job? We actually measured, now we heard today that the incandescent lamp is 4% efficient. 4%, changing electricity to light. 96% goes off as heat. The electron beam process, interestingly enough, we actually measured a 72% efficiency from the socket to chemistry in the water. That's pretty good. It's about 7 times better than the efficiency of ozone, for example. So we actually had a pilot plant in Miami where we would measure the total power into the plant. We would do the chemistry and the engineering, and in fact, we were getting 72 kilowatts of chemistry out of 100 kilowatts at the plug. That's not bad. That's actually a very efficient process. The problem was, and the showstopper at the time, was the fact that the capital investment was relatively high. And it depends on how you look at the total economics, because that's what stopped everybody. At that point, which was now in the mid-90s to the late 90s, we were dealing with a plant that cost $1.7 million capital, and we were able to treat 120 to 150 gallons per minute of water at a pilot plant scale, but it was at a real wastewater treatment plant. And everybody would say, well, how are you going to scale that up? And we just say, well, you just put parallel systems in. And of course, they'd laugh at you. And I've been laughed at quite a bit, so that's all right. But interestingly enough now, because there's a friend of mine over in Korea that's pretty smart, he's actually come up with new ways and new technologies in the electron beam area that have lowered the capital cost by almost fourfold. So now we're starting to think that maybe we need to look at this, because the capital intensity of this process is much less. Interestingly enough, the O&M of this process is probably the cheap O&M's operation and maintenance of this process is probably in fact the cheapest of many of, if not all of, the advanced oxidation processes. In fact, we have a mobile tractor trailer that we built to take the beam to the problem. The electron accelerator that's in that trailer was built in 1963. And about 3 or 4 months ago, we ran an experiment down in Orlando. It took us, and after the beam had been sitting in a parking lot, literally in a truck, in a parking lot in Washington, D.C. for 2 years, it took us 2 days to get it up to the original manufacturing specifications. And it ran like a champ for the week or two of the process. So here's an electron beam that was built in 1963, and here it is 2007, and it's actually still running according to the manufacturer's specifications. So the point is, I think here, as engineers at universities, we must think outside of the box. We have to start thinking in terms of these innovative processes. This is a good example of where over the last 20 years the capital cost, because it's not actually ever been implemented except in one plant in the world, but Boom Soo Han, my friend in Korea, is trying to get it implemented. The capital costs have come down, and the O&M costs are very good. And I think the real tie-in with this particular conference is the fact that this particular process runs at a measured efficiency of about 72%. And even if I was cheating a little bit, which of course I do, 50% is still 10 times better than an electric light bulb. So I think it goes without saying that this actually is a rather energy efficient process. So I'm not going to go into this. This is really just too boring, and we're getting tired. I will say, though, that, well, just to give you an idea, I do kinetic models, and we do some things that we play with these all sorts of differential equations. I couldn't differentiate myself out of my seat, actually, but luckily for computers, it makes me sound like I know what I'm doing. In the areas of interest, I think are interesting, and this is where it comes into water reuse. One of probably the biggest areas that are calling water reuse into question are these areas of emerging contaminants of concern. And there, depending on which list you look at, there may be 400 different chemicals that are of interest and that are on the radar screen, and I'm sure that there will be more that will come onto the radar screen. But these are things such as personal care products, hormones, steroids, antibiotics, pharmaceuticals, et cetera, et cetera. And the one thing that we do know about these compounds is that they all, well, let's say at least the hormones, steroids, and the antibiotics, they're developed because they do have health effects. Whether they're adverse as far as we're concerned in drinking water, that's another question, and that's one that we hope to learn through cell bioassays, actually. When we disinfect water, we use chlorine, ozone, chloramines. Over 600 chemicals have been identified as byproducts of this process. Many of them have very, very low concentrations, and that very low concentrations is exactly where a process like the electron beam process or many advanced oxidation processes actually become economically viable. High volumes, low concentrations, very difficult to get rid of those compounds at low concentrations with things like aeration stripping or carbon adsorption. So I think there is in our portfolio of water in the future a high interest in advanced oxidation processes. I don't think I'm going to go into that end of it. I really do believe that we're getting tired. And because I can't get into the higher energy excited state because Arturo keeps me at the lowest singlet state, we're going to kind of keep moving on this. And so economic models. I have a problem with economic models. Not only do I not understand them, I don't use them, except they always seem to come back and bite me in the butt. And I believe that many of them, but I do know enough that I believe that many of the models that we use today are going to be inadequate to predict how we will solve problems of tomorrow. And I've tried to engage the economists at UCI to think about new ways and develop new economic models, and they're really resistant. In fact, I was actually pretty abusive to them at one lunch when I just told them that, you know, I think all these economic models that you guys have suck. It didn't endear me to them, but it certainly, we had a very interesting and lively conversation. I think actually John did a nice job of this idea of looking at life cycle costs. And I think that's really, really important. And I think we still are looking at life cycle costs too narrowly. I think we need to expand our thoughts about that. Our evaluation of ecosystems. I think, again, John mentioned the fact that the ecosystems are in there in that model. I think that's absolutely essential. Because as I said, and I believe, that not only is water absolutely essential for us, it's essential for a healthy planet. And I would hope that we would engage that in our thinking, that that's as important as anything else is. And I think this MBA model of thinking about the next quarter or the CEO the next year or the next decade is also got to be rethought. And I think we need to think in terms of centuries. I'm sure that most of us have or will have children or grandchildren, as some of us do, and you'd like to think that you're going to actually leave a legacy that's going to make it a little bit better for them. And I think that if we continue to think about the next fiscal quarter or the next year or the next 4 years, as most elected, or 6 years if you're in the Senate, we need to think, really, really think hard about expanding those. So I think there needs to be a paradigm shift in policy. Now I'm really getting onto shaky grounds. So if we and scientists and engineers are to develop real solutions, and I think we can, there has to be a large shift in the policy approaches to problems. We have to get around the command and control prescriptive solutions that EPA likes to those, to arrive at those solutions that make sense. Now there's a lot of negatives in there because we also have to engage the industry and our industrial partners into thinking about things beyond the next quarter. To do this, we have to educate the public, develop adequate risk assessment procedures, and rewrite some of the less than operable procedures that have been set in place. And I'm thinking specifically in terms of Superfund here. What an abysmal failure. Great idea, but it didn't work. And I think this ties back into the economic models and where companies should be rewarded for doing the right thing. After all, if we think of the biggest polluter, or one of the biggest, is the U.S. government, you know, the question is can we slap the hands of Uncle Sam? So with that, I really would like to finish and try to get us somewhat back on a time, and I hope maybe that some of these thoughts may stimulate some discussion.
Anyway, this is sort of a tongue-in-cheek statement, but this plant has been operating for about a year, and it's the Edison's newest thermoelectric plant. It's a combined cycle. What I'm going to talk about today is sort of describe the plant, the cooling water sources for the plant, use of reclaimed water, the water treatment and recovery system. I got a lot of pictures, so not too many words. And then what do I see for what we're going to be doing in the future for water cooling, and cooling at power plants. This little map over here is just an inset. The plant's located, nestled next to San Bernardino and the city of Redlands, California. You all heard about combined cycle. My picture's way better than Bob's picture, by the way. the one thing I wanted to add that Bob didn't say is that combined cycles are way more efficient than Rankine cycle or the old boiler type plants, coal-fired plants, oil plants. They're way more efficient, and as such, that's good. So for this amount of fuel, you get this much more energy with this kind of plant. So this is a nice advancement, and these plants, as the years go on, I worked for Edison a long time ago. I worked there for about almost 10 years, and we designed the first combined cycle plant. We actually put 2 of them in the 70s. I mean, these have been around for a really long time, and they have been getting progressively more and more efficient. A lot of them are built in California because we don't build coal plants in California, and so the guy from the Energy Commission's laughing. But we don't build coal plants in California, and this is good for California because, like I said, you get a lot more power for the same amount of fuel. Little bit about the plant itself. These are units 3 and 4. Units 1 and 2 were retired. They're very old plants, and they've been decommissioned. There are 1,000 megawatts of power. There's 2 units. These are called 2x1 combined cycles. You have 2 gas turbines. Each gas turbine has what is known as a heat recovery steam generator or a boiler. It takes that hot gas, recovers it, you generate steam, and then those 2 steam turbines operate, or those 2 boilers make steam for 1 steam turbine. So you got 2 gas turbines, 1 steam turbine. Okay, this is a unique plant. This is a one-of-a-kind in California in that it uses reclaimed water and contaminated groundwater, which is kind of cool. If you think about it. The groundwater is from the San Bernardino Basin. It's also called the Bunker Hill Basin for some strange reason. Anyway, but it's part of a big regional basin. It's part of just a natural drainage from the mountains. The plant's right up against the mountains. The groundwater's been contaminated with primarily perchlorates from rocket engine and rocket fuel testing over many, many, many years. Perchlorate is a very, very stable molecule. It just goes in one end, comes right out the other, and it's way more concentrated when it comes out the other end. So the cooling towers, like you've heard, they represent 85 to 95% of the water. This plant uses 1/3 the amount of water of a comparably sized Rankine cycle plant for cooling, because only 1/3 of the megawatts are driven by steam turbine. Therefore, you have 1/3 of the water demand. And the average water demand is about 3,300 gallons a minute. That can get up to almost 5,000 gallons a minute in the summertime when it's really hot. A little bit about reclaimed water. 40 years ago, the city of Burbank got this crazy idea to use reclaimed water, and they actually did it. And they really were at least pioneers in California. It's been used a lot in other states, primarily in the Southwest. That includes Arizona. Texas and Florida have used reclaimed water. 10 years ago, I was involved with a project in Klamath, Oregon, where we were going to look at reclaimed water, and they told me, well, who's using this stuff, and is it dangerous? So, health, because God knows where it comes from. I mean, that's the thought. So we looked at it, and I said, geez, there's a couple places in Florida, and there's Burbank, and there's hardly anybody that's using it, a couple places in Texas. There are hundreds of plants now, literally hundreds of plants. I mean, when you submit an application for a power plant in California, the first thing that's asked is, so where's the reclaimed water for this cooling tower? I mean, that's just the way it is now, okay? Now you use reclaimed water, it's not a big deal. When I went to the Palo Verde nuclear generating station when I worked for Southern California Edison, because we wanted to see what they had to do to use this thing. And it was a huge treatment plant, and it was over-treated. I mean, there really weren't any kind of chemicals to help prevent corrosion and scaling and stuff. So they ended up treating the heck out of it. Now they're very common. People use it a lot, and it's not a big deal anymore. Right now in California, there's one plant that when they use reclaimed water, they really use it. It goes in one end and it comes out as salt at the other end, and that's the Magnolia Power Plant, City of Burbank. Palo Verde Nuclear Generating Station, they also use it, and of course, Mountain View Power Plant. Okay, this is kind of the how it's divvied up at the plant. Right now, last year they averaged almost exactly 50-50. They use slightly more contaminated groundwater than reclaimed water. The one thing about reclaimed water that you have to remember is it's way saltier, it's got stuff in it, it's got organic matter in it, and it creates problems with scale and corrosion, which is a big deal in a power plant, a big deal in a power plant. That thing that's underneath the steam turbine that cools the steam to condense the steam, corrosion's bad. Scaling is bad because it makes those tubes less efficient. They get plugged, they get fouled. The plant becomes less efficient and uses more energy to make the same number of megawatts, okay? The groundwater, again, is perchlorate contaminated, and I said about the perchlorate molecule. So the one thing about this water, and this one part of the slide was wrong, I didn't catch it. The plant, if we didn't have this treatment system, the plant would use this water, and they would probably cycle it 4 or 5 times. They're cycling an equivalent of about 11 times now with this water. Now what they do is the water, all the plant wastewater, it's not a zero discharge plant, it's sort of a near zero discharge plant. There's a stream of wastewater that's left over. It's very saline. It's got all the stuff that was in the water, including the perchlorate, which basically works its way all the way through. And that goes into what is known as the Santa Ana Regional Interceptor. Now, the Santa Ana Watershed Project basically put this collection system together to take industrial wastewater from the watershed so it wouldn't contaminate the groundwater, interestingly enough. 40 years ago, 35 years ago, I went to a meeting. They were trying to solicit people to, hey, sign on and jump on this line and we can take your wastewater away from you. What that line does, it provides a very good function. It takes all the water all the wastewater generated, including taking nitrate contaminated groundwater and desalting it. It takes all that water and it takes it all the way to the Orange County Sanitation District. It's a long pipeline from San Bernardino, the San Bernardino area, all the way out of it goes out of the basin and eventually to the ocean. There's a little bit of fresh groundwater that's used, and that's just used for some high-quality plant uses. Okay, cooling tower. Bob so eloquently described how they work. I'm not going to really go into a lot of detail, other than the fact that you have the issues, again, are that water cycles up in the tower. The term is called cycling up. As you evaporate water, the salts stay behind. It gets more concentrated, more concentrated. You have to bleed the tower, and that's called the blowdown. The plant has inserted in the cooling circuit a water reuse system. And what it does is it takes what is known as a slipstream. It takes a little bit of the water that's circulating around and around the cooling towers, and it treats it. And it has basically 2 levels of treatment. The first is just basic minerals removal, calcium, magnesium, a little bit of silica. And then the second phase is really the desal piece to it. That little dashed line in the middle of that box there distinguishes those 2 phases. You can see there the water leaving goes to sorry. Now, if we didn't have this plant, the blowdown would be much, much greater. The waste stream would be much, much greater. Okay, this is sort of an overview of the plant, of the system. This is what how the system's put together. It's got a reactor clarifier, sometimes known as a solids contact clarifier, a softener. This basically takes out calcium, magnesium. It ends up making sort of a slurry-looking stream, which is thickened, and that is just a dry sludge cake that is hauled all the way to the middle of California to Buttonwillow for disposal. And that's because it has perchlorates in the solids material. From there we go to gravity filter. A portion of that goes straight to the cooling towers. From there we go to gravity filters. We go to weak acid cation exchangers, sometimes known as ion exchangers, water softeners. It's an acid cycle water softening process. then what happens is all the hardness goes in there, gets removed. The hardness is exchanged for hydrogen ions. The water gets very carbonaceous. It goes into what is known as a gasifier, just an air stripper. CO2 comes off, and then it goes into the reverse osmosis system. And this is a two-stage system. It's also configured as a two-pass system, which is another way of sort of configuring it up. But basically, this desalinates the water to a pretty high quality. Some of the water goes back to the cooling towers. Other is used in other parts of the plant. All the wastewater that's generated here from the weak acid cation exchangers creates a very acidic wastewater that is neutralized, and that goes into the slurry line as well. Now for the pictures. See, this is not going to be so bad after all. Okay, this is the reactor clarifier. And it looks really brown and ugly in the middle because we have to add ferric chloride. That's not the reclaimed water, okay? We have to add ferric chloride, and that gives sort of a brownish color. And so this sort of, where it's really bubbly and stuff, that's a little problem we have with the reactor clarifier that we have to fix. That's Steve Johnson. He's the technical manager for the plant. He's here, and that's one of his favorite problems at the plant right now. Like, we little entrapped air in there. This thing is about 45 feet in diameter, something like that. Its capacity is 2,000 gallons a minute. Water comes into the middle, mixes up. It's recirculated around and around for contact and stuff, contact time. It comes out of what they call a skirt, and it rises, and it's very clarified, very, very clarified. In the background there, you can see the thickener, that sort of tank thing back there. This screen looks terrible standing here. It looks great over there. This over here, that's the thickener, and that basically takes the sludge that comes out from the bottom. That's called sludge. It's about 3 to 5%, and it thickens up, and it's actually a way to store it as well. Next this is what they call the launder or trough. This is where the water that comes out that's been clarified. This looks pretty good. It goes into the trough, goes out, and then it goes either straight to the cooling towers, or it gets further treatment for desalination. This is the filter press. The sludge comes up into this thing. It's got all these leaves, one after another, like this. And between each leaf, the leaves are basically, it's a little chamber. It's got cloth on the chamber. The sludge goes into that cloth, and the water pushes through the chamber, leaving all the solid material behind. And then when it's all full, you can't push any more in there. Pull one leaf apart at a time in this big slab of cake. And it's not the cake you want to eat, but it's this big slab of dried salt comes out of it. It's quite interesting. This is the gravity filter. This is a very common piece of equipment. This is found a lot in especially municipal facilities. This takes the water that has a little bit of particulate matter in it, and it just filters it really well. Upstream of the weak acid softeners, and these are about 8 feet in diameter, 20 feet tall. They're about half filled with this ion exchange material, and this is where the heart of the process is. Without this, no desalination. What we do here is we take all the calcium, magnesium, barium, strontium, any divalent ions have to be removed from it. These remove that. They go through the this is the neutralization system for the WAC ion, because it's an acidic process. We go through the decarbonator tower. Now what this does is it takes the CO2 out. Once the CO2 is out, we blow air through the bottom. You got this really carbonaceous water. It falls through this packing, and it mixes with the air, and the CO2 comes off. The CO2 wants to just leave. Once the CO2 is out, we jack the pH up to about 10, 10 and a half. So you got to have no hardness present whatsoever, because there's still some silica in this water, and it creates some big problems. Then we go to the RO, and this is these ROs will take 600 gallons a minute each. Each bank will take. There's 2 banks of them, and they basically desalinate the water to a pretty high quality. So what's left over is the RO reject, and it's a very briny stream. It's all this water, all concentrated down. Water's gone. Just the salts are left. So this plant is sort of, like I said, it's unique in that it's using contaminated groundwater. It's kind of one of a kind. I don't think I know there's not another one in California. I'm not sure about other places in the country, but it's very, very unique in that respect. Some things for the future, and a lot of these things have been said already. There is going to be more. Reclaimed water is here, and it's going to be used for power plant cooling, and that's not even, nobody even says, geez, can we do that? It's just an accepted fact. The next things are going to be saline groundwater and produced water. I do a lot of work in the area of produced water as well. Every time you pull up a barrel of oil, you get 9 to 10 barrels of water, and some of this water can be very, very salty. And I've spent the last 12 years in Bakersfield trying to figure out how to use this water, just in the oil fields alone. I mean, not to mention for reclamation. I worked with the DOE on a project in New Mexico looking at this water. So this is becoming, it's a resource. It comes out of the ground, and they usually stick it right back down to the ground again. So it's a resource that's there, and I think that's going to be in the future somehow. Desalination plants, we talked about them. The interesting thing about power plants and desalination plants, you can put one right next to a power plant. They need power. You know, I know they're inefficient. They're the best we got right now. And there are some projects right now. There's one that's being considered in Huntington Beach. The Encina plant in San Diego is also considering this combination. Once-through cooling in California is really going to become a thing of the past, I think. I mean, the plants that are there now are concerned about just the rules and the regulations that EPA's putting forth, that they can't, it's going to be difficult to meet them. And I think that's going to be the next step is no more once-through cooling in California. And I just put this last one in here because I saw a really cool presentation at a DOE meeting where they were looking at taking water out of flue gas from a power plant, because you get a lot of water, you know. It's a byproduct of combustion. So anyway, that's the presentation. There's the plant. Isn't it pretty?